University of California, Fall 2008 Chemistry 8A presents Electronegativity.
Good evening. Our discussion this evening is about the fascinating topic of electronegativity. Electronegativity is how strongly an atom is able to pull electrons towards it, and therefore its ability to make partial or full charges when forming bonds. In order to visualize this phenomenon, let us now pay a visit to our team, who are ready with a highly technical demonstration.
Now this here is an oxygen atom locked in combat with two hydrogen atoms to establish dominion over their electrons. Let's see what happens next. Crikey, that oxygen is strong!
The electronegativity of an atom can be determined using the periodic table. It increases from left to right and from bottom to top. Fluorine is therefore the most electronegative atom. Now let's look at this concept in action.
In this methane molecule, electronegativity is not significantly different between carbon and hydrogen. The electrons are thus shared equally by all participating atoms. Each equal bond is called a nonpolar bond, and methane as a whole is a nonpolar molecule.
In water, on the other hand, oxygen is more electronegative than hydrogen, so it will pull electrons toward it. The bonds between oxygen and hydrogen are polar bonds, and water is a polar molecule. Oxygen will have a partial negative charge because the negative electrons are closer to it, and hydrogen will have a partial positive charge. Polar molecules have unique properties due to their partial charges. The intermolecular forces are different, as we will see later.
Ethane contains only nonpolar bonds because carbon and hydrogen do not differ significantly in their electronegativity. Ethanol, however, contains an electronegative oxygen, which has a partial negative charge when compared to both the adjacent carbon and hydrogen. This polarity gives ethanol substantially different properties than ethane, such as the capacity for hydrogen bonding and a higher boiling point.
I'm polar!
So, what forces can act on a molecule? There are several types of intermolecular force, but we will focus on the three that best illustrate electronegativity. The first is van der Waals interactions. The weakest form of intermolecular force, these interactions are caused by momentary partial charges, not due to polarity, but simply to the constant motion of electrons, and thus their temporary presence or absence in a given region of an atom. To this model, we go to our trained experts, Jackie and Mary. How fascinating. The second type of intermolecular force is dipole-dipole force. Polar molecules have continuous partial charges, and so the positive and negative regions of different molecules can attract one another. These forces are stronger than van der Waals interactions. With another example, here are Jackie and Mary. Thirdly, we look at a special case of dipole-dipole interactions, hydrogen bonding. Molecules with hydrogens and either oxygen, fluorine, or nitrogen are capable of hydrogen bonding. Essentially, an especially strong dipole-dipole force, these are the strongest intermolecular forces that are not actual bonds. Because there is more electronegativity, difference between atoms, the partial charges are more extreme, which allows molecules to attract each other even more. One last time. Here are Jackie and Mary.
Mary!
These bonds are stronger, but they can still be broken by the application of heat. So what makes electronegativity so interesting and important? Well, it is everywhere, from South Africa to your glass of water.
As we discovered earlier, water contains electronegative oxygen, making polar bonds and thus a polar molecule. We also now know that because there are oxygen and hydrogen, water molecules are capable of hydrogen bonding. When water is a liquid, hydrogen bonding occurs between molecules, breaking and reforming as they move past each other. When water is cooled, molecules move more slowly and get closer. However, once crystalline ice is formed, each water molecule hydrogen bonds to 4 other molecules, as opposed to the 3.4 on average in liquid water. This phenomenon is responsible for the incredible fact that ice is less dense than liquid water. The bond angle is increased and thus leaves gaps between molecules. This is why your ice cubes float, and aquatic life can survive an Arctic winter beneath the ice layer.
But what makes this different from this and this? The answer is DNA. DNA is the basis of almost all life on Earth. It's a genetic code for all organisms and some viruses, perfectly suited to its information storing role because of its structure. Watson and Crick's famous double helix structure for DNA depends heavily on different intermolecular forces.
The backbone of the DNA, alternating phosphates and sugars, is held together by covalent bonds, making it very stable under many conditions. The attractions between nucleotide bases, on the other hand, are due to hydrogen bonding. T and A bases are held together by 2 hydrogen bonds, while G and C are held together by 3. The fact that hydrogen bonds are sturdy but are still able to separate and reform is vital for DNA to replicate or be translated to the proteins in our bodies.
As you can see, electronegativity is a formidable force, so to speak. It is vital to our way of life, and not to be overlooked. For one final message, let's go to the rest of our team.
Enjoy responsibly.